In the beginning, there was an agreement, silent, ancient, and absolute. Matter would exist, and gravity would hold it close. From the birth of the first stars to the slow turning of galaxies, this covenant shaped everything. The curvature of space, the rhythm of time, the balance between chaos and order. It was a trust so fundamental that even light bowed to it. But across the farthest reaches of the universe, something begins to drift. Galaxies move away faster than their own mass should allow. Their light stretches thin, red, and tired, as if fleeing an unseen command. The equations still hold, yet the meaning behind them begins to tremble. Gravity, once loyal to matter's weight, appears to be losing faith. This betrayal is not sudden. It is quiet, patient, a rebellion written in the empty spaces between galaxies. The force that built the stars now seems to turn away from them, following a deeper, darker logic. Scientists give it a name: dark energy. But the name only deepens the mystery, for what they describe is not a presence, but an absence, a pressure without origin, an expansion without end. If gravity is no longer listening to matter, what is it listening to? If space-time itself begins to move without cause, what hidden truth has awakened within its geometry? The universe, once bound by the oldest trust of all, now drifts into uncertainty, as if the cosmos itself has begun to forget why it ever held together at all. What remains when gravity stops believing in matter, and the laws that once shaped reality begin to question their own existence? In the quiet years after Einstein's great revelation, that space and time are not separate realms but a single, pliable fabric, the universe seemed at last to make sense. Gravity was no longer a mysterious force acting from afar. It was geometry itself, the bending of space-time under the weight of matter. Every star, every planet, every wandering atom followed that curve faithfully, pulled not by invisible strings, but by the elegant warping of reality. For a time, this vision appeared complete. Yet even as the equations of relativity found their way into textbooks, a young astronomer named Edwin Hubble stood on a California mountaintop and saw something that would make the cosmos restless again. Using the 100-inch Hooker telescope at Mount Wilson Observatory, Hubble observed faint smudges of light, nebulae as they were called then, and measured their distance using the pulsations of certain stars known as Cepheid variables. What he found shattered the stillness of the known universe. Those smudges were not part of the Milky Way. They were other galaxies, vast island universes, each receding from us, their light stretched by motion. The farther they were, the faster they fled. The universe, Hubble realized, was expanding. At first, this revelation was seen as a kind of poetic symmetry, a cosmos born in motion, carried forward by momentum, still guided by gravity's patient hand. Over time, matter would pull against this expansion, slowing it, balancing the outward rush with the inward tug of attraction. Gravity was the great equalizer, the reminder that even in infinite darkness, everything still belonged to something. But that belonging would not last. Decades passed. Astronomers charted the large-scale structure of the cosmos, filaments of galaxies, clusters bound together like frozen lightning across the void. The assumption remained simple. Gravity, born of mass, must slow the cosmic expansion over time. Every calculation, every model leaned on that certainty, until the light from distant dying stars began to tell a different story. In the late 1990s, two independent teams of scientists, the High-Z Supernova Search Team, led by Adam Rees and Brian Schmidt, and the Supernova Cosmology Project, led by Saul Perlmutter, set out to measure the universe's deceleration. They chose Type Ia supernovae, the cosmic beacons that flare when a white dwarf star steals too much matter from its companion and collapses in a thermonuclear blaze. These explosions burn with near-uniform brightness, allowing astronomers to calculate their true distance by comparing how bright they appear from Earth. Each data point was a message from billions of years in the past, a record of how fast space was expanding when that light began its journey. If gravity's pull were winning, distant supernovae should appear slightly brighter, closer than they would be in a universe speeding up. But as the teams compared data from opposite hemispheres, a quiet disbelief took root. The supernovae were fainter than expected, far fainter. The conclusion was unavoidable and absurd. The universe was not slowing down. It was accelerating. At first, the idea seemed too radical to accept. Gravity, by its very nature, should resist expansion. The very notion that the universe was speeding up implied the presence of a force that repelled rather than attracted, a cosmic pressure pushing space apart. The astronomers checked their instruments. They recalibrated their telescopes, recalculated the distances, questioned the reliability of the Type Ia standard candles. But the more they corrected, the clearer the message became. Space itself was stretching faster and faster with time, and so, reluctantly, cosmology entered an era of doubt. The data pointed toward an unknown energy filling all of space, invisible, undetectable, yet unimaginably powerful. It did not behave like matter or radiation. It could not be clustered or confined. It simply was, everywhere, always, pushing. They called it dark energy. The term carried the weight of humility, a label not for understanding, but for the absence of it. In physics, dark does not mean evil. It means hidden, unseen, a placeholder in the equations for something vast and silent. The discovery shook the foundations of modern science. Einstein's general relativity, though magnificent, had not predicted this. The cosmological constant, a term he once inserted into his equations to keep the universe static, then later called his greatest blunder, suddenly returned as a possible explanation. If a constant energy pervaded the vacuum of space, it could account for the acceleration. But if Einstein had been right all along, the implications were staggering. The energy of the vacuum, the empty space between galaxies, between atoms, between quarks, would not be zero. Nothingness, it turned out, was not truly nothing. It had weight, pressure, consequence, and yet the numbers refused to cooperate. When physicists tried to calculate the vacuum energy from quantum field theory, the result overshot observation by an unimaginable margin, 120 orders of magnitude too large. The most disastrous mismatch in all of science. Somewhere between the infinities of the quantum world and the curvature of relativity, the universe was hiding its truth. For the first time since Newton watched an apple fall, gravity itself came into question. Not its presence, but its faithfulness. If gravity was supposed to bind, why was the cosmos slipping through its fingers? The old image of gravity as an eternal guardian no longer held. It was as if space-time had begun to listen to something deeper than matter, a hidden rhythm, a secret pressure beneath the visible. The galaxies, each containing hundreds of billions of stars, drifted not because they chose to, but because the stage beneath them was swelling. The fabric of space was expanding not into something, but of itself. A self-replicating emptiness, accelerating its own unfolding. Dark energy was not confined to the outskirts of galaxies. It lived everywhere, in every cubic meter of vacuum, in every silent corner of the cosmos. Even here, between the molecules of breath, its invisible hand extended, immeasurably faint but utterly pervasive. If it were slightly weaker, the universe would collapse back upon itself. Slightly stronger, and galaxies would never have formed. The balance was so precise that it defied randomness, a tuning so delicate that physicists began to whisper of fine-tuning, of anthropic principles, of universes beyond our own. The discovery changed more than numbers in a model. It changed what it meant to know the universe. For centuries, matter had been the anchor of existence. From the planets that could be touched to the stars that could be measured, everything was built on something tangible, measurable, massive. Now that foundation had cracked. Roughly 70% of the universe, it seemed, was made of something that could not be seen or touched, something that did not emit or absorb light, a cosmic presence responsible for accelerating the expansion of all things. Dark energy was not merely a new ingredient, it was a new language, one that described a universe no longer ruled by the visible, but by the invisible. Gravity's story was no longer simple attraction. It had become a paradox. The universe's most loyal force now caught in a quiet betrayal of its own laws. In meeting rooms and observatories around the world, scientists spoke in tones of disbelief and wonder. Saul Perlmutter would later describe how no one expected to see acceleration. They were looking for deceleration, for proof of gravity's dominance. Adam Rees recalled nights staring at data that refused to yield to expectation. Brian Schmidt compared the feeling to standing at the edge of a cliff and realizing The ground beneath was no longer stable. What they had uncovered was not an answer, but a rupture. A realization that the universe was more dynamic, more alive, and more uncertain than anyone had dared to imagine. This was not merely a change in numbers or constants. It was a change in trust. The old cosmic order, where gravity and matter moved in perfect accord, was gone. In its place stood a riddle so vast that even light struggled to escape its implications. The cosmos was expanding, and that expansion was speeding up. The universe had entered a phase of rebellion against its own weight. The deeper meaning lingered in the silence between equations. If gravity no longer held matter close, what force was pulling it apart? What purpose could acceleration serve in a universe so finely balanced? Some saw it as evidence of something beyond physics. A hint of multiverses, of different regions of existence where the laws themselves varied. Others viewed it as nature's reminder that knowledge, like gravity, is never absolute. And somewhere, beneath the vast orchestration of galaxies and light, an invisible current carried everything forward. A current that could not be seen, but could be felt in the numbers, the light curves, the maps of the cosmic web. It was as if the universe itself had taken a breath, a long, slow exhale into infinity. The discovery of dark energy did not end the story of cosmology. It began a new one, a story not of certainty but of doubt, a story where the most fundamental force of all seemed to hesitate, to waver, to drift away from the matter it once obeyed without question. And in that hesitation, the universe revealed its most human truth, that even the laws of nature can falter, that even the oldest bonds can bend under the weight of mystery. Gravity, it seemed, was no longer sure of what it believed in. And from that moment of doubt, the cosmos began to rewrite its own story. In the centuries that followed Newton's revelation, gravity was the most faithful of laws. It did not falter. It did not hide. It bound the planets in their patient orbits, carried comets through frozen darkness, and governed the fall of every apple and every star. Its language was simple, its reach infinite. Even as the universe expanded, gravity remained the quiet promise that, in time, everything would still listen. But when the accelerating universe emerged from the data, when light from distant supernovae whispered that expansion was speeding up, not slowing down, that promise began to fracture. It was a small change in the numbers, but an enormous wound in the story of physics. Because if the universe was accelerating, then space-time itself was moving in ways matter did not command. And for the first time in modern science, gravity appeared faithless. According to Einstein's general relativity, the dance of existence follows a sacred geometry. Matter tells space-time how to curve, and curved space-time tells matter how to move. This dialogue defined everything from the orbit of Mercury to the birth of galaxies. But in the late 20th century, the universe began to speak a new dialect, one in which space-time seemed to curve on its own, without matter's instruction. The galaxies were not just drifting apart, they were fleeing, as if some unseen tide beneath the fabric of the cosmos was pulling them outward, expanding every gulf of darkness faster and faster with time. Einstein had once considered such a possibility, to prevent his equations from predicting a collapsing or expanding universe, something unthinkable in his day. He introduced a mathematical term, the cosmological constant, a small, static pressure that kept the universe balanced, neither shrinking nor stretching. Later, when Hubble discovered the expansion, Einstein removed it, calling it his greatest blunder. But now, decades after his death, the blunder had returned, and this time, it might be the only thing keeping the equations from collapsing entirely. In laboratories and observatories, disbelief turned into obsession. Physicists recalculated the balance of matter in the cosmos, the luminous stars, the drifting dust, the invisible clouds of dark matter. But none of it added up. There simply wasn't enough gravity to explain what they saw. The universe's acceleration implied that some strange energy pervaded the vacuum itself, a kind of negative pressure that opposed gravity, turning expansion into runaway flight. This mysterious agent was soon given a name, dark energy. Yet the name was less an explanation than an admission of defeat, a confession that the universe had begun behaving like a stranger in observatories scattered across the mountains of Chile and Hawaii, at Cerro Tololo, at Keck, At Hubble, high above the clouds, astronomers turned their gaze deeper into space. They looked back billions of years into the infancy of galaxies to see if there had been a moment when gravity's trust began to fail. But every image brought the same answer. The acceleration was everywhere. Always. There was no starting point, no wound to trace. It was as if the betrayal had always been there, waiting to be noticed. The deeper they looked, the more uncanny the cosmos became. If dark energy truly filled the vacuum, it meant that empty space was not empty at all. It hummed with invisible energy, a field woven through every cubic centimeter of reality. Quantum field theory had hinted at this, that the vacuum was not a void, but a sea of virtual particles, blinking in and out of existence at unimaginable speeds. Yet when physicists tried to calculate how much energy such a vacuum would have, the numbers spiraled into absurdity. The predicted vacuum energy was 120 orders of magnitude larger than what the universe displayed. Mismatch so catastrophic that it became known as the worst calculation in the history of science, somewhere between the infinitesimal mathematics of the quantum and the sweeping geometry of relativity. Something refused to fit. It was not just a question of physics, it was a question of trust. The cosmological constant, once a forgotten term, became both a savior and a specter. It could explain the acceleration, yes, but it did not explain why. Was it a fixed property of space-time, or a dynamic force changing with time? Was it the energy of the vacuum, or the whisper of a hidden field? Each answer fractured into more questions. In theoretical halls at Princeton, Stanford, and Cambridge, the debates grew more philosophical. The cosmological constant seemed to work, but it felt wrong, too arbitrary, too convenient. Einstein's equations had been resurrected not with understanding, but with resignation. A patch sewn over a wound that no one could name. Even the word constant felt dishonest. If the vacuum's energy could drive expansion, could it not also change, fluctuate, or fade? Some cosmologists proposed quintessence, a dynamic field that evolves over time, a cosmic fluid that ebbs and flows as the universe grows. Others suggested that perhaps Einstein's equations themselves needed rewriting, that gravity at the largest scales was not what it seemed. It was an age of disbelief, not because scientists lacked faith in data, but because the data revealed a universe that no longer followed reason. Observations deepened the unease. The cosmic microwave background, the ancient afterglow of the Big Bang, captured by satellites like COBE, WMAP, and Planck, offered the most precise map of the early universe ever made. In its faint ripples of temperature, scientists saw the fingerprints of gravity and expansion written across space-time itself. And in those patterns, dark energy's hand was unmistakable. Its presence was not confined to the present day. It had been shaping the universe for billions of years, accelerating its expansion long before the first stars had finished burning. It was woven into the geometry of existence. Not a recent rebellion, but an ancient decision. The numbers were relentless. About 68% of the universe was made of dark energy, 27% of dark matter, and less than 5% of everything visible. All the stars, planets, and life combined. The cosmos, it turned out, was built mostly of things it refused to show. For many, the discovery was less enlightening than existential. If the universe's acceleration continues indefinitely, then galaxies will drift farther and farther apart until the night sky goes dark. Communication between cosmic islands will end. The light from distant clusters will stretch beyond visibility, and even the memory of other galaxies will fade into silence. This is not merely expansion, it is isolation, a slow unraveling of cosmic companionship. Some scientists began to speak of the cosmic horizon, a limit beyond which light will never reach us, no matter how long we wait. Beyond that line, the universe slips away forever. Each year, a little more of it vanishes, not in destruction, but in disconnection. It is a strange fate for a universe once born in fire and unity, to die not by collapse, but by loneliness. And yet the deeper the despair, the stronger the curiosity. If gravity had not failed, but changed, if space-time itself had evolved new rules, then, understanding that transformation might reveal truths about reality no equation had ever touched. Some theorists proposed that dark energy might be a property of the quantum vacuum, a constant energy density intrinsic to space itself. Others suggested it might emerge from extra dimensions, curled and unseen, influencing the expansion of our visible universe. A few speculated that it could even be a form of cosmic feedback, space-time reacting to its own curvature, learning, adapting. For all its mystery, dark energy obeyed one clear rule. It was consistent. It filled the universe evenly, its pressure constant across all of space. No void was too empty, no galaxy too dense to escape its touch. It was everywhere. And in that omnipresence, it felt less like a force and more like a mood. In quiet observatories, late at night, astronomers continued to search for signs of its origin. Through the lenses of the Keck telescopes, through the mirrored eyes of Hubble, they peered into galaxies whose light had traveled 10 billion years. Each faint glimmer was a record of cosmic expansion written across time. And always, the same truth returned. Gravity's grip was weakening, not in strength but in purpose. The universe, once held together by attraction, was now defined by separation. The trust between matter and space-time, the silent harmony that had held since the first atoms formed, seemed to have dissolved into something colder, more distant. The galaxies no longer obeyed the geometry of the past. They moved to the rhythm of something else, something beyond mass, beyond motion, beyond comprehension. This was the era of disbelief, an era when equations whispered of ghosts in the vacuum, when telescopes revealed not answers but absences, when the most fundamental force of all began to feel less like a law and more like a memory. For the first time, science faced a universe that seemed to have outgrown the language written for it. And yet, beneath the confusion and the fear, there was wonder, the quiet awe that comes when mystery deepens instead of resolves. Because in that mystery lay the next frontier, the next great story the cosmos had yet to tell. If gravity had begun to ignore matter's instructions, perhaps it was listening to something deeper, a voice that had always been there, faint but eternal, echoing through the geometry of space itself. A voice that whispered not of order or chaos, but of change. The universe, it seemed, was not rebelling. It was evolving. In the cold elegance of mathematics, the universe once seemed obedient. Every mass curved space, every curve commanded motion. Gravity was the silent arbiter between matter and the void, a promise written in the geometry of Einstein's field equations. But as physicists peered into the abyss between the quantum and the cosmic, that promise began to dissolve. The universe, it seemed, could no longer be explained by a single language. One spoke of smooth curves and warps in space-time, the poetry of general relativity. The other murmured in probabilities and fluctuations, the restless dialect of quantum mechanics. Each, perfect within its realm, collapses in the presence of the other. And in that collapse, a fracture opens, the place where equations lose their anchor. In the 1960s and 70s, as quantum field theory matured, theorists began to calculate what empty space should be, not a void, but a restless ocean of energy. Particles blinking in and out of existence, fields shimmering with invisible motion. Every point in space, according to quantum physics, should contain a staggering density of vacuum energy. If gravity obeyed quantum logic, that invisible pressure should tear space-time apart in an instant. Yet the cosmos persists, vast, stable, expanding slowly enough for galaxies to form, stars to shine, and life to question it all. When physicists compared the theoretical energy of this vacuum to the faint acceleration observed by astronomers, the difference was incomprehensible. Not by a few factors, not even by a trillion, but by a number so absurd it defied language. A discrepancy of 1 followed by 120 zeros. It was called the cosmological constant problem, and it remains the most catastrophic failure in theoretical physics. Einstein's equations, elegant and unbroken, demand a cosmological constant, a value that tells space-time how to curve even in the absence of matter. But when that constant is fed quantum predictions, the equations unravel. The universe, if it followed those numbers, would explode outward in less than a heartbeat. Something, somewhere, is cancelling almost all of the vacuum's fury, leaving only a whisper behind, just enough to nudge galaxies apart. Yet no one knows how or why. Steven Weinberg, one of the architects of modern quantum field theory, tried to make sense of the unthinkable. He suggested that perhaps there is nothing unique about the value of this cosmic constant. Perhaps countless universes exist, each born with a different balance between gravity and vacuum energy, some expanding too fast for galaxies to form, others collapsing before light could shine. Only in a rare few would the constant take a value gentle enough for stars, chemistry, and consciousness to arise. And in that rare universe, observers would naturally ask why it was so. It was not design, he argued, but selection, a cosmic lottery of existence, a principle both humbling and hollow. The anthropic argument. But others found no comfort there. Andre Linde envisioned a multiverse of eternal inflation, a cosmic sea where new universes bubble endlessly into being. Each pocket, a different set of laws, a different fate. Gravity in this vision is not universal law, but local custom. Its loyalty, like that of a changing wind, belongs to the physics of each particular world. Leonard Susskind took the idea further. He saw the multiverse not as a flight of imagination, but as an inevitable consequence of string theory, a framework that replaces point-like particles with vibrating strings of energy. Each vibration, each compacted extra dimension gives rise to a different possible vacuum, each with its own constants and forces. The result is a landscape of possibilities so vast that our universe may be one grain of sand among 10 to 1,000 others. Within such immensity, the notion of gravity's universality begins to dissolve. Perhaps gravity does not believe in matter. It simply adapts to the version of existence it finds itself in. Yet even this cosmic multitude fails to comfort the equations. For all its elegance, string theory remains incomplete, untested, a theory of everything that explains nothing observable yet. And so physicists turn their gaze inward, toward the foundations of space-time itself. A quiet revolution began to stir. What if gravity is not fundamental at all? What if it is emergent, a side effect of something deeper, something woven not from matter or energy, but from information? Erik Verlinde, a Dutch theoretical physicist, proposed a radical idea in 2010. He suggested that gravity might arise not as a fundamental force, but as a consequence of entropy, the universal drive toward disorder. Just as heat emerges from countless molecular motions, gravity might emerge from the statistical behavior of microscopic bits of information encoded in space-time. In this view, mass does not bend space. Information does. The universe, at its core, may be a self-organizing computation, a hologram of entropy unfolding through time. The implications ripple through the foundations of physics. If Verlinde is right, then Einstein's curvature and Newton's attraction are illusions of a deeper thermodynamic truth. Space and time are not the stage upon which reality unfolds. They are byproducts of something far more primal, information interacting with itself. And in that hidden ocean, gravity is no more sacred than temperature, no more fundamental than pressure. The vacuum, then, is not empty. It is a restless ledger of cosmic information, bits recording the ever-shifting balance between what is known and what can never be. If matter disappears from the story, gravity would not grieve. It would simply reconfigure, following the logic of entropy rather than the loyalty of mass. A cosmos without matter might still bend, still expand, still evolve, because the fabric beneath remains alive with statistical motion. It would be a universe where geometry itself dreams of matter rather than the other way around. But this vision too comes with unease. If gravity is not real, only emergent, then perhaps space-time itself is an illusion, a tapestry projected from the boundaries of the universe, as suggested by the holographic principle. In that idea, first glimpsed through the paradoxes of black hole thermodynamics, the three-dimensional world might be a projection from a two-dimensional surface beyond our comprehension. Every galaxy, every atom, every heartbeat, encoded like a shadow on the edge of existence. Black holes whisper this truth most clearly. Their event horizons carry entropy, the measure of information hidden within. Stephen Hawking and Jacob Bekenstein showed that this entropy is proportional not to volume, but to surface area. In the most extreme gravity known, the universe hints that reality itself may not be volumetric. The cosmos, perhaps, is a hologram that believes itself to be solid, and so the crisis deepens. The equations still stand, yet their meaning grows hollow. Gravity works, planets orbit, light bends, but the foundations tremble beneath them. Every experiment confirms relativity's predictions, yet every deeper question dissolves into paradox. What then does gravity trust, if not matter? What keeps the cosmos bound, if not the mass within it? In the quiet halls of CERN, in the data streams of the Planck satellite, in the mirrored eyes of the James Webb Space Telescope, scientists continue to measure, the cosmic microwave background, the clustering of galaxies, the subtle lensing of light through invisible filaments of mass, each observation confirms the same truth. Gravity behaves as though something unseen fills the universe, something that neither shines nor collides, something that bends space without caring for atoms. Dark energy drives expansion, dark matter holds galaxies together, and between them, ordinary matter, everything humans can see or touch, makes up less than 5% of the total. In that imbalance lies the echo of betrayal. Gravity, once thought to be the servant of matter, now seems devoted to the unseen. It curves for the invisible, accelerates for the unknown, and leaves the visible world adrift like dust on a forgotten sea. Perhaps, some theorists muse, this is the natural order. Perhaps matter was never the master, only a brief condensation of deeper fields. The universe may be built not from particles, but from information and geometry, energy and vacuum, the intangible scaffolds that precede form. In such a cosmos, gravity does not lose faith. It merely remembers where it truly belonged. And yet the question lingers, heavy, unresolved, like a faint hum beneath the stars. If gravity is emergent, if space-time itself is a mirage, what then is real? Is the universe built upon illusion, or is illusion the only way reality can exist at all? Physicists calculate, satellites observe, equations evolve. But the paradox remains, a quiet reminder that understanding may not be the same as knowing. In the end, gravity's disobedience may not be rebellion, but revelation. Perhaps, when equations lose their anchor, they are not falling apart. They are pointing somewhere deeper, beyond mass, beyond curvature, beyond even space and time, toward the invisible truth that binds everything still. The deeper humanity looks into the night, the more it realizes how little is actually there. What was once thought to be a luminous universe, a grand cathedral of stars, nebulae, and galaxies, turns out to be a thin shimmer over an invisible abyss. The cosmos, in its full account, is missing almost everything. Only about 5% of it glows, reflects, or interacts with light. The rest, more than 95%, is unseen, silent, and almost indifferent to the senses. This revelation did not arrive suddenly. It unfolded over decades of doubt, through the quiet persistence of evidence that refused to fit. Astronomers had long believed that galaxies were held together by the gravity of their stars and gas. But when Vera Rubin in the 1970s traced the rotational speeds of galaxies, the numbers betrayed expectation. Stars at the edges moved too fast, far beyond what visible matter could bind. If only the seen existed, those galaxies should have torn themselves apart. Yet they held firm, as if anchored by a weight no one could see. Rubin's results at first were met with disbelief, but then the pattern repeated, again and again, across galaxy after galaxy, cluster after cluster. The invisible mass was real, not imagined, not an error. It was something that made up far more of the universe than everything known. The name given to this unseen matter was simple, almost poetic in its emptiness: dark matter. It neither emits nor absorbs light. It does not collide, ignite, or decay. It simply exerts gravity, shaping the cosmos like a sculptor working in shadow. As new telescopes opened their eyes to the sky, Hubble, Chandra, Keck, astronomers began to map the invisible by its influence. One of the most haunting portraits came from a celestial collision known as the Bullet Cluster. Two galaxy clusters, each a titanic congregation of stars, gas, and dark mass, had slammed through one another at millions of kilometers per hour. In the visible spectrum, the hot gas between them glowed in X-rays, a luminous shockwave of ordinary matter. But gravitational lensing, the bending of background light by mass, told another story. The lensing maps revealed that most of the mass was not where the visible gas lay. It had passed straight through, unbothered by the collision, invisible but immense. Ordinary matter had been slowed, heated, scattered. Dark matter had drifted onward, ghost-like, indifferent to friction. It was a silent witness to catastrophe, untouched by it. In that image, a veil of blue lensing halos floating apart from red clouds of gas, the universe confessed its secret. Gravity itself seemed to be listening to something unseen. The bullet cluster became one of the clearest proofs that dark matter was real. Not a trick of gravity, not a flaw in Newton's laws, but a dominant player in the cosmic structure. From the formation of galaxies to the growth of cosmic filaments, dark matter was revealed as the skeleton of creation. Luminous matter, the stars and planets and people, were mere traces clinging to its invisible frame. And yet, even with dark matter accounted for, the universe still refused to behave. In 1998, two teams studying Type Ia supernovae, cosmic explosions used as standard candles, found that the expansion of the universe was accelerating. Instead of slowing under its own gravity, space was stretching faster with time. No known force could cause this. The missing energy needed to drive such expansion was vast, enough to dominate the entire universe. This invisible pressure was named dark energy. Unlike dark matter, it was not a substance, but a property of space itself, an outward push, smooth and uniform, woven into the vacuum. It did not cluster or collapse. It simply accelerated, everywhere and all at once. Together, these two dark entities, matter that cannot be seen and energy that cannot be measured, account for nearly the whole of existence. What humanity can touch, weigh or see is less than the margin of error. The cosmos, once thought to be a grand interplay of stars, turns out to be governed by a ghostly majority. Matter, it seems, is not what gravity listens to anymore. The relationship has inverted. The visible now follows the invisible. From the vantage of deep sky surveys, the large-scale structure of the universe looks like a web. Filaments of galaxies stretched across billions of light years, separated by vast cosmic voids. This cosmic web is not random. It traces the gravitational imprint of dark matter, the scaffolding upon which galaxies assemble and evolve. Without it, no stars would have formed, no galaxies would have condensed, no cosmic architecture would exist. Simulations like the Millennium Run and Illustris have shown how this unseen framework weaves the universe together. By feeding computers with the laws of physics and varying the balance of matter and energy, astrophysicists can recreate the cosmos from its earliest moments. The results match the real universe only when dark matter and dark energy are included. Without them, galaxies drift too loosely, cosmic filaments fail to form, and the expansion unravels. The dark components dictate the dance. Luminous matter merely follows, tracing their gravitational choreography like faint sparks along invisible strings. Even light, the purest messenger, is bent by their will. Through gravitational lensing, entire galaxies appear stretched, mirrored, multiplied. Optical illusions born of unseen mass. Every distorted arc in the night sky whispers of something vast and silent bending the rules of perception. In 2013, the European Space Agency's Planck satellite mapped the cosmic microwave background, the oldest light in the universe, a remnant from when the cosmos was only 380,000 years old. Embedded within that ancient glow were faint temperature, ripples, tiny variations that record the seeds of all future structure. By analyzing those patterns, scientists could read the universe's composition like a fossilized code, and the message was clear. Only about 4.9% of the cosmos is made of baryonic or ordinary matter. About 26% is dark matter. Nearly 69% is dark energy. Everything visible, galaxies, stars, planets, and the chemical story of life emerges from a statistical rounding error in the cosmic balance. The universe is, by every measure, almost entirely made of things that cannot be seen or touched. And so, the question deepens. What is mass if so little of it glows? What is gravity if it obeys forces we cannot detect? Perhaps, some physicists whisper, humanity never truly understood what mass meant at all. There are competing visions of what this dark universe might be. Some propose that dark matter consists of weakly interacting massive particles, WIMPs, relics from the early universe that linger unseen, passing through stars and planets by the trillions every second. Others suggest ultralight axions, ghostly fields that ripple gently through the cosmos. Still others turn to sterile neutrinos, particles that never engage with normal matter except through gravity. Particle detectors buried deep underground, like the Xenon 1T experiment in Italy or the LX Zeppelin in South Dakota, wait in perfect silence for one of these elusive particles to strike. Years pass, data accumulates, but so far, nothing. No flash, no interaction, no confirmation. Dark matter remains hidden, faithful to its name. Dark energy, meanwhile, defies even this level of speculation. It could be Einstein's cosmological constant, a property of the vacuum itself, or a dynamic field that changes with time, like a cosmic tide rising and falling over eons. The data fits the former for now, but the truth may yet shift. In some models, dark energy might decay. In others, it could eventually reverse, pulling everything back together in a final collapse. Either way, it governs the universe's fate, a silent hand writing its ultimate sentence. Philosophically, it is a staggering inversion. For centuries, matter was reality, tangible, measurable, the very substance of existence. Now, it is background noise, a luminous residue adrift in a sea of shadow. Gravity, once thought to be a servant of matter, now appears loyal to something else. Something deeper, more abstract, perhaps even more fundamental. The visible cosmos, magnificent as it is, may be little more than a reflection of unseen principles, geometry, or hidden dimensions. In this sense, the universe's structure becomes an act of faith, not of human belief, but of nature's own invisible conviction. When astronomers peer into the faintest galaxies, they see time itself stretched thin. Some of the light now reaching Earth began its journey when gravity still obeyed the visible world. But as it crosses the expanding void, it passes through epochs where that trust faltered, where dark energy began to dominate, where matter's influence waned. The story it tells is not of chaos, but of replacement. Gravity did not vanish. It simply chose a new partner. And so, the cosmic disappearing act continues. The deeper humanity searches for the universe's substance, the more it finds absence. Light bends around shadows. Stars obey forces they cannot see. Equations yield answers that describe nothing familiar. The universe, it seems, hides its meaning behind invisibility itself. Perhaps this is not deception, but design. Perhaps visibility was never the goal. The cosmos may not need to be seen to exist, only to be measured, inferred, felt through its gravity. It could be that the universe has always been led by a phantom hand, one that neither light nor matter can trace, yet upon which all existence depends. In the end, the mystery of dark matter and dark energy is not just scientific, it is existential. The stars that fill the sky, the atoms that build worlds, the light that carries every image and thought, they are not the foundation. They are the exceptions. The cosmos does not shine because it is made of light. It shines because, against overwhelming darkness, it chooses to. And somewhere, beyond the veil of the visible, gravity listens, not to matter, not to light, but to the silent geometry that has always ruled the night. In the dark geometry of the cosmos, there exists a place where all theories tremble, where equations reach their breaking point and logic bends like light near a star's dying breath. It is here, at the edge of a black hole, that gravity turns inward, against itself. At first, it begins as collapse, the slow, inevitable surrender of matter to its own weight. A massive star, once burning with fusion's delicate balance, reaches exhaustion. No longer able to resist the inward pull, its outer layers implode in a final, catastrophic sigh. Within seconds, the atoms that once forged elements and light are crushed beyond recognition. Their mass no longer belongs to matter, it belongs to gravity. What remains is a singularity, a point with no size, yet infinite density, where the known laws of physics dissolve. Einstein's equations, which once described the smooth flow of space-time, now spiral into infinities. Quantum mechanics, with its probabilistic certainties, collapses under the weight of its own definitions. Space folds, time halts, and what was once a star becomes a region from which not even light, the messenger of the universe, can escape. The boundary of this invisible abyss is called the event horizon. It marks the point of no return, where escape velocity equals the speed of light. Beyond it, causality unravels. The very idea of before and after loses meaning. And yet, the story of a black hole is not one of pure destruction. It is also the story of resistance, because here, gravity, the architect of the trap, encounters its most persistent adversary, quantum mechanics. In 1974, Stephen Hawking performed a calculation that forever changed our understanding of black holes. By applying quantum field theory to the curved spacetime surrounding an event horizon, he found something astonishing. Black holes are not perfectly black. They glow. Tiny fluctuations in the vacuum, pairs of particles and antiparticles constantly flickering in and out of existence, are influenced by the immense gravity. One particle may fall in while its partner escapes, carrying away a trace of energy. Over eons, this process, known as Hawking radiation, causes the black hole to slowly evaporate. The prison that gravity builds is not eternal. The walls it forges can crumble, not through force, but through information. This discovery ignited a paradox, perhaps the greatest in theoretical physics. If a black hole evaporates, what happens to the information it contained? Quantum mechanics insists that information can never be destroyed. Yet general relativity, unyielding in its geometric certainty, implies that all traces vanish into the singularity. For decades, physicists wrestled with this contradiction, the information paradox. It is not merely a question of data, but of the universe's fundamental logic. If information can disappear, then predictability collapses, and with it, the very fabric of cause and effect. To solve this, physicists began to suspect that space-time itself may not be what it seems. In recent decades, a profound idea has emerged that the universe might be holographic. This holographic principle, developed from the work of Gerard 't Hooft and Leonard Susskind, proposes that everything within a volume of space can be described by information encoded on its boundary. Just as a two-dimensional hologram encodes a three-dimensional image, reality itself may be the projection of information inscribed on a cosmic surface. Nowhere does this idea find stronger footing than in black holes. According to the work of Jacob Bekenstein, the entropy, or informational content, of a black hole is not proportional to its volume, but to the area of its event horizon. Every bit of information that falls in seems to leave its mark, faint but permanent, on the surface that hides the singularity. If true, this means that the universe itself may work in the same way, that gravity, space, and time, the pillars of Einstein's universe, are not fundamental at all, but emergent, like heat arising from molecular motion, or pressure emerging from countless unseen collisions. Gravity may emerge from something deeper, from the collective behavior of quantum bits of information. In this view, space-time is not continuous. It is granular, woven from the smallest possible units of entropy, the Planck-scale pixels of the cosmos. The smooth curvature described by relativity is only an illusion, a large-scale shadow cast by the microscopic interactions of invisible information. In 2010, Dutch physicist Erik Verlinde advanced this radical idea. He suggested that gravity is not a force, but an entropic effect, the natural result of information-seeking equilibrium. Just as heat flows from hot to cold, gravity may emerge from the universe's tendency to maximize entropy. A falling apple is not pulled by an invisible force. It simply follows the statistical gradient of information encoded in spacetime. Under this light, the black hole becomes not a monster, but a teacher. It demonstrates that the laws of the cosmos are not immutable, but emergent, rising from patterns deeper than geometry, deeper even than matter. If space-time is informational, then gravity's role is to shape how that information flows. Matter is no longer the source of gravity. It is its shadow, a manifestation of the way information arranges itself in the fabric of the universe. This redefines the very meaning of existence. The familiar idea of substance, of things having intrinsic mass, gives way to something more subtle. Perhaps mass is not a property, but a process, an echo of information moving through a deeper medium. Black holes, once thought to be the graveyards of matter, may instead be archives, storing, encoding, and eventually re-releasing the information of everything they consume. When a black hole evaporates through Hawking radiation, it does not erase what it swallowed. It transforms it, returning the information to the universe in scrambled form. Yet even this resolution carries mystery. The precise mechanism of how information escapes remains one of physics' most profound questions. The work of physicists like Juan Maldacena, who developed the ADES-CFT correspondence, suggests that the holographic principle might indeed preserve information perfectly. In his model, a black hole in a higher dimensional space can be fully described by quantum interactions on its lower dimensional boundary. A universe within a universe, both real, both equivalent. If this is true, then the universe we observe may itself be a hologram projected from the boundary of a deeper reality. And in that deeper reality, gravity is not a ruler of matter, but a language, the way information speaks across scales. In the end, gravity's apparent self-destruction inside a black hole may not be destruction at all. It is metamorphosis, a shedding of its old identity as a fundamental force, to reveal a truer self, a messenger of information, an echo of entropy's eternal dialogue. The singularity, that forbidden point of infinite curvature, may not even exist in the way we imagine. Quantum gravity, the long-sought theory uniting general relativity and quantum mechanics, could smooth it away, replacing the impossible point with a finite, complex structure of quantum states. Loop quantum gravity, for instance, imagines space-time as a vast network of loops, each carrying discrete units of area and volume. In such a universe, collapse might never reach infinity, only transformation. Even string theory, that grand web of vibrating dimensions, offers its own resolution. It replaces the singularity with the collective harmony of strings, not points, but extended entities whose vibration patterns encode the properties of particles and space-time itself. In all these visions, one truth remains. Gravity cannot destroy itself because it is not an independent thing. It is the behavior of the universe's most fundamental memory, the way information curves, folds, and whispers to itself across time. So, when gravity devours matter and bends light into silence, it is not ending anything. It is remembering. It is reorganizing information into new forms, preparing to release it again when the cosmos calls. What began as a battle, gravity against quantum physics, begins to look more like a reconciliation. Each side describes the same story from different scales, one from the cosmic, one from the microscopic. Where they meet at the event horizon lies the boundary not only of space-time, but of human understanding. And yet, even in that silence, something remains. The faint glow of Hawking radiation, the soft, persistent hum of information escaping gravity's final embrace. It is the sound of the universe correcting itself. Gravity, once the most certain of all forces, now stands revealed not as master, but as servant, a phenomenon born from the deeper grammar of existence. It has not betrayed matter. It has evolved beyond it, and in that evolution, the universe may finally be learning to understand itself. In the long corridors of modern physics, two great languages whisper past each other. One speaks in the smooth, continuous curvature of space-time, Einstein's masterpiece of geometry and inevitability. The other murmurs in the staccato rhythm of uncertainty, quantum mechanics, where the world dances in probabilities and the smallest particles flicker in and out of existence. Both describe reality with exquisite precision, and yet they refuse to agree. When placed together, their equations fracture, their logic collapses. The gravity that shapes galaxies cannot speak to the quarks and photons that make them, and the quantum world, so restless and vibrant, cannot explain how space bends beneath the weight of a single star. This is the fracture at the heart of physics, a silent wound between two truths. To mend it, scientists have spent decades chasing a single dream, a unified theory, a description of reality so complete that gravity and quantum fields are revealed not as rivals, but as reflections of one another. The search has led to some of the most daring visions ever conceived, theories in which gravity loses its loyalty to matter and becomes something stranger, more abstract, more self-aware. String theory, the music beneath reality. In the 1970s, a bold idea began to shimmer on the mathematical horizon. What if the universe was not built from point-like particles at all, but from tiny vibrating strings, filaments of energy, each oscillation giving rise to a different particle? In this view, the electron, the photon, even the graviton, the hypothetical quantum of gravity, are all musical notes in a vast cosmic symphony. The strings vibrate not in 3 dimensions, but in 10 or 11 hidden dimensions curled so tightly they evade detection. Their harmonies define the laws of physics. Their resonances weave the very fabric of space-time. Gravity, in this picture, is not an external force, but an emergent rhythm. It arises from the collective vibration of these strings, as if space-time itself were a song, a structure born from resonance. String theory elegantly predicts the existence of the graviton, something no other quantum theory of gravity has achieved. It also suggests that the universe may contain countless parallel realities, the multiverse, each defined by a different way the strings vibrate. Some universes might have stronger gravity, others weaker, others no recognizable matter at all. For some physicists, this idea is intoxicating, a vision of infinite possibility, a cosmos that endlessly recomposes itself. But for others, it feels like gravity slipping away into abstraction. Because string theory, despite its beauty, offers few predictions we can test. Its equations describe a universe that might be true, but might also be forever beyond observation. Gravity, in this vision, becomes faithless not out of defiance, but out of transcendence. It no longer needs matter to define it. It hums in dimensions unseen, beyond experiment, beyond proof. Loop, quantum gravity. The geometry of the invisible, where string theory reaches outward into extra dimensions, another path turns inward, to the smallest possible scale, where even space itself might be made of discrete pieces. Loop quantum gravity begins with a simple question. What if space-time is not continuous? What if it comes in quanta, tiny loops of geometry, woven into an invisible network at the Planck scale? In this framework, space is granular, composed of countless interlocking rings, each carrying a fragment of area and volume. Together, they form the weave of space-time, a cosmic fabric that shimmers with quantized tension. Gravity here is not a field or a force. It is geometry itself, arising from how these loops connect and twist. Just as a rope appears smooth from afar but reveals its threads up close, space-time may appear continuous only at human scales. Zoom in far enough, and the illusion breaks. Reality becomes a tapestry of quantum knots. Loop quantum gravity offers one of the most elegant resolutions to Einstein's singularities, where general relativity predicts infinite density inside a black hole, or at the Big Bang, loop theory softens the edges. At the smallest scale, the loops resist collapse, preventing the infinite. In some models, the Big Bang becomes a big bounce, the rebound of a collapsing universe giving birth to a new one. It is a universe that repairs itself, a cosmos where gravity never truly destroys but transforms. But even here questions remain. The theory, though conceptually powerful, has yet to link completely with the world we see. Its predictions lie beyond the reach of our instruments, its quantum loops too small for light to touch. And so, like string theory, it too asks for a kind of faith, the belief that geometry itself breathes, that space is alive with invisible architecture. Modified gravity, the universe with changing rules. For some, the answer may not lie in quantum depths or hidden dimensions. Perhaps gravity is not broken at all, only misunderstood. In the 1980s, physicist Mordechai Milgram proposed a radical alternative, modified Newtonian dynamics, or MOND. He noticed that galaxies spin faster than their visible mass should allow, an observation usually attributed to dark matter. But what if, he asked, there is no dark matter? What if gravity itself behaves differently at vast cosmic scales, weakening more gently than Newton's law predicts? MOND reproduces many galactic rotation curves without invoking invisible matter, suggesting that gravity might simply change its behavior with distance. Later, other theories expanded on this idea: FR gravity, TVES, and other modifications of Einstein's equations. Each attempts to explain cosmic observations without resorting to unseen entities. But as telescopes sharpened their view, dark matter continued to assert its presence through gravitational lensing and the cosmic microwave background. Modified gravity could explain parts of the mystery, but not all. Still, these theories hint at something profound, that gravity may not be a single, universal law. It could be fluid, dynamic, adapting to the scales it governs. Like a storyteller changing tone with audience, gravity may speak one language in galaxies, another among atoms, and another still in the empty dark between. Dark energy and the faithless expansion. While physicists debated the nature of gravity on small scales, the universe revealed a larger betrayal. In 1998, observations of distant supernovae uncovered a shocking truth. The expansion of the universe is accelerating. Rather than slowing under its own gravity, space itself is pushing outward faster and faster, driven by an unknown force now called dark energy. Einstein once introduced a cosmological constant, a term that would keep the universe static, only to discard it when cosmic expansion was discovered. Now that constant has returned, reinterpreted as vacuum energy, a pressure inherent to space-time itself. Quantum field theory predicts that even empty space seethes with energy from virtual particles flickering into existence. But when physicists calculate this vacuum energy, the result overshoots observation by a factor of 10^120, the most catastrophic mismatch in all of science. It is as if gravity and quantum mechanics are looking at the same ocean, but one sees a ripple while the other sees a storm. Dark energy, in its quiet persistence, might be the universe's final act of independence, space-time no longer pulled by mass, but driven by its own expansion. Gravity, once the keeper of order, becomes the passenger, no longer the captain. In this strange new cosmos, the gravitational pull of matter is drowned out by the repulsive pressure of the vacuum itself. Galaxies drift apart. The stars that once spoke to each other in gravity's voice fall silent. In time, even light will fail to cross the expanding gulf. The universe grows cold, vast and faithless, not in malice, but in inevitability. The fractured faith, each theory, string, loop, modified gravity, dark energy, tells a different story about a universe searching for coherence. Each offers a metaphor for gravity's changing faith. In string theory, gravity is the music of hidden dimensions. In loop quantum gravity, it is the geometry of woven space. In modified gravity, it is a law that adapts to the stage it governs. In dark energy, it is the echo of the vacuum itself, a pressure without origin, a will without substance. But none can answer the question that haunts them all. Why did gravity stop believing? Why does the force that binds the cosmos refuse to fit within our equations? Why does it bend space flawlessly on galactic scales, yet defy quantization at the smallest? Why does it obey the universe's structure, yet seem to emerge from something deeper, something not entirely real? Perhaps gravity never betrayed matter. Perhaps matter betrayed the deeper truth, that it was never the foundation at all. That beneath the atoms, beneath the fields, beneath even the strings and loops, lies a code, an informational law that does not need mass to shape it. Gravity, in this light, is not faithless. It is free. It is the universe's way of remembering itself, bending not because of what exists, but because of what information demands. And so, the search continues, not to tame gravity, but to understand what it is trying to say. Each equation is a verse, each experiment a whisper in the dark, until one day perhaps, the universe will reveal its final confession, that gravity was never a force at all, but the memory of connection, the quiet geometry of belief that holds the cosmos together, even as it slips from our grasp. In the modern age of cosmology, the search for truth no longer begins with parchment and pen, nor ends in the lonely gaze of a telescope beneath the stars. It begins underground, in vast rings of metal and light, in tunnels that hum with energies once reserved for the birth of universes. It begins in the stillness of mountain caverns, in mirrors cooled to near absolute zero, listening for whispers from the fabric of space-time itself. It begins, in short, at the edge of nothing, where gravity, matter, and meaning blur into the same unspoken question. If gravity no longer behaves as it once did, if it has turned its gaze away from matter, then humanity's task is no longer to observe, but to summon the impossible, to rebuild, in miniature, the conditions that first bound the universe together. The great machine beneath Geneva. beneath the border of Switzerland and France lies a circle 27 kilometers wide. The Large Hadron Collider, the most complex instrument ever built by human hands. Here, protons race at nearly the speed of light, guided by superconducting magnets colder than outer space itself. When they collide, the energy of their impact recreates the first trillionth of a second after the Big Bang, a time when gravity, electromagnetism, and the nuclear forces may have been one. Since its first run in 2008, the LHC has revealed particles long predicted but never seen. The Higgs boson, the giver of mass, the silent architect of structure, but it has also deepened the mystery it was built to solve. If the Higgs field endows matter with weight, then why does gravity, which should respond to that weight, behave so differently across scales? Why does space-time expand faster even as matter resists? Some theorists whisper that the collider's collisions might someday produce micro-black holes, fleeting distortions of space-time that could reveal the existence of hidden dimensions, unseen corridors where gravity disperses its strength. So far, no such signs have appeared. But in the silence of its detectors, physicists still listen, chasing anomalies buried in trillions of collisions. Because if gravity is leaking into other dimensions, then the faintest deviation, the smallest imbalance in energy, might be the first trace of its defection. The LHC is not merely a scientific instrument. It is a cathedral of uncertainty, built to interrogate the invisible. Every pulse of energy, every whisper of a quark, is a question. Where does gravity end and the rest of reality begin? The eyes that map, the invisible high above the collider's tunnels, the search continues in the vast silence of space. There, telescopes do not smash particles together. They watch what the universe itself has already done. The Euclid telescope, launched by the European Space Agency, is one such eye. Its mission is not to look at stars, but at what lies between them, the dark geometry of cosmic structure. By mapping the shapes and distortions of billions of galaxies across 10 billion years of history, Euclid traces the invisible fingerprints of dark energy. Every faint distortion, every subtle warp of light, known as weak gravitational lensing, carries information about how space-time bends. If gravity were changing, if its strength or allegiance shifted over time, the pattern of these warps would betray it. In this way, Euclid is less a telescope than a seismograph of the void, measuring the tremors of cosmic expansion itself. Soon it will be joined by NASA's Nancy Grace Roman Space Telescope, a next-generation observatory with an eye 100 times wider than Hubble's. Roman will map the large-scale structure of the universe with exquisite precision, measuring how galaxies cluster, drift, and disperse under the rule, or rebellion, of gravity. Both missions share a singular purpose: to find where the universe's trust began to fray. If gravity is losing faith in matter, the evidence will not come in the form of sudden explosions or cosmic cataclysms. It will appear as the faintest asymmetry in the pattern of light, a quiet misalignment in the geometry of existence. Listening to the fabric of space-time, while telescopes watch the cosmos in light, another generation of instruments listens to it in motion. They do not see, but feel. In 2015, a century after Einstein predicted them, gravitational waves were finally detected, ripples in space-time caused by colliding black holes. For the first time, humanity heard the universe not through photons, but through the trembling of its very structure. Now, observatories like LIGO in the United States, Virgo in Italy, and Kagra in Japan form a global network of ears pressed to the cosmic fabric. Kagra, buried deep within the mountains of Kamioka, is the quietest of them all, an instrument so sensitive that it can detect distortions smaller than a single proton. Its twin laser beams, reflected between mirrors chilled close to absolute zero, measure the stretching and squeezing of space-time itself. These detectors are more than marvels of engineering. They are experiments in philosophy. For what they measure is not sound, not light, but change itself, the universe's pulse, written in the language of curvature. When two black holes collide, they create ripples that travel through the cosmos, warping distances as they pass. But some physicists believe that these waves might carry deeper secrets. Perhaps hidden in their subtle echoes are signs that space-time is not smooth, that gravity itself is quantized, granular, imperfect, or that the waves lose coherence, leaking energy into hidden dimensions. If such deviations were found, They would mark the first direct evidence that gravity is no longer bound to the universe we know, that it has begun to echo across realities unseen. Laboratories of silence. The most haunting experiments. However, do not chase collisions or cosmic explosions. They dwell in stillness. In laboratories cooled to near nothing, where atoms are frozen in perfect alignment, physicists attempt to weigh the unweighable. Projects like the EOT Wash experiment at the University of Washington test gravity at sub-millimeter scales, searching for any deviation from Newton's law that might reveal hidden forces. Tiny torsion balances, suspended by fibers thinner than a hair, detect the faintest shifts in attraction. If gravity weakens, strengthens, or fluctuates at these scales, it would suggest that something else, something unseen, is shaping the relationship between mass and space. Elsewhere, quantum physicists entangle particles separated by vast distances. Watching how information passes instantaneously between them, they wonder whether gravity too could be entangled. Not a classical force, but a quantum correlation between the smallest units of space-time. In 2022, experiments at Fermilab and Delft University began probing this question, using entangled qubits to test whether gravity can transmit quantum information. If confirmed, it would mean gravity itself emerges from the same ghostly fabric that binds entangled particles, not a law imposed on matter, but a property arising from information. Such experiments, quiet and small, strike at the heart of the cosmic question. They seek the moment when gravity stopped believing in matter, or perhaps when matter stopped being the thing that gravity listened to. Messages cast into the dark every collider beam, every frozen atom, every telescope orbiting the void, all are messages written in equations and light, cast into the dark. Each seeks a reply from a universe that no longer answers as it once did. If gravity has changed, if it has slipped beyond our comprehension, these machines are our final attempt to understand the silence. They are not mere tools, they are confessions of belief, for behind every accelerator and detector lies a fragile hope that the cosmos, despite its coldness, is still a conversation, and perhaps it is. Perhaps in the noise of collisions or the faint trembling of space-time, the universe is still speaking, but in a language too vast for us to yet decipher. Even failure here is meaningful. When the LHC finds no new particles, when Euclid detects no shift, when Cagra hears only the same steady hum of space-time, each null result still sharpens the truth. Each quiet answer marks the boundary between what the universe will reveal and what it keeps hidden. The experiments grow larger, more ambitious, as if humanity believes that scale itself can coax gravity back into conversation. The next collider, the future circular collider, will stretch 100 kilometers. Space-based interferometers like LISA will orbit the Sun, measuring gravitational waves across millions of kilometers. Together, they form an ever-expanding architecture of faith, a belief that somewhere, at some scale, the universe will let its mask slip, the edge of nothing. All these instruments, from the cold steel of Geneva to the silent mirrors of Japan, from orbiting telescopes to quantum labs, point toward a single truth. Humanity is standing at the edge of nothing, asking questions of the void. It is not the first time. The same question once haunted Newton beneath his apple tree, Einstein beneath the stars, and Hawking beneath the shadow of a black hole. What is gravity truly? A force, a geometry, a memory of connection? Now, in the age of dark energy and vanishing matter, that question becomes more urgent and more personal. For if gravity is not loyal to matter, then the universe itself is not what it seems. It is not built from things, but from relationships, from the quiet interplay between information, curvature, and time. Every experiment is an act of reaching, a hand extended into a darkness that may never reach back. Yet the reaching continues, because somewhere in that darkness, in the silence between collisions and the whisper between waves, lies the origin of everything that ever held together. And perhaps, if the instruments are patient enough, if the questions are pure enough, the universe will respond once more. Not with noise, but with a faint and almost imperceptible shift. A sign that gravity still remembers, that even at the edge of nothing, belief endures. In the slow breath of cosmic time, even eternity has an ending. The stars, once the storytellers of matter and heat, begin to tire, One by one, they fade, leaving behind a quiet too vast to measure. The light that once bridged the distances between galaxies begins to stretch, red shifting into invisibility, its wavelength elongated by the accelerating expansion of space-time. What remains is not darkness, but something deeper, a dimming of meaning itself. The universe, as observed by cosmologists and simulated through the equations of LCDM, the lambda cold dark matter model, is not static. Its expansion is speeding up, driven by something unseen, a pressure that works against gravity's ancient pull. This phenomenon, known as dark energy, makes up nearly 70% of all that exists. It has no texture, no direction, no detectable field lines. It simply is, a quiet, accelerating breath that pushes the cosmos apart. In this cosmic future, galaxies once bound in clusters begin to drift. Gravity, once the faithful architect of order, can no longer keep them tethered. Each cluster becomes an island of light, separated by an ocean of ever-widening void. Astronomers predict that in about 100 billion years, distant galaxies will move so far that their light will never reach us again. The universe will appear empty, its expansion swallowing even the memory of what came before. The Milky Way and Andromeda, destined to collide and merge long before that age, will form a single elliptical galaxy, one last citadel of starlight, but beyond its borders, nothing will remain visible. Future observers, if any could exist, would see only their own galaxy floating in perfect solitude, unaware that there were once trillions of others. For them, cosmology would end not in revelation, but in amnesia. The universe will have forgotten itself. Within these isolated galaxies, the rhythm of creation will slow. Star formation, which today ignites in molecular clouds dense with hydrogen, will falter as the gas supply dwindles. The last generation of stars, small, long-lived red dwarfs, will burn dimly for trillions of years. When they finally fade, the night will be filled only with the cold embers of dead suns, white dwarfs cooling into black. Physicists call this the degenerate era, an epoch when the universe will be composed almost entirely of the remnants of what once was. Black holes, neutron stars, and dark frozen spheres. Even then, gravity will still shape the remnants of galaxies, drawing matter into quiet spirals around invisible centers. But even that loyalty will not last forever. For black holes, those last monarchs of gravity's reign, hold within them the final act of defiance and the final act of surrender. According to Stephen Hawking's calculations, black holes emit radiation due to quantum effects at their event horizons. It is a whisper of heat, faint beyond comprehension, but it carries a terrible prophecy. Over unimaginable spans of time, 10 or 100 years or more, even the most massive black holes will evaporate, dissolving into a thin mist of photons. Gravity, once the keeper of cosmic memory, will watch as its greatest creations fade into nothing. The last echoes of curvature, the final remnants of space-time's sculpted geometry, will smooth into uniformity. The universe will approach what physicists call heat death, a state of maximum entropy, where no gradients remain to drive motion, no differences to birth time. The equations that once described galaxies and clusters will reduce to silence. Temperature will fall toward absolute zero. No stars, no light, no thought. Just the faint hum of virtual particles flickering in and out of existence. Quantum ghosts haunting an infinite void. And yet, even here, in this final stillness, there are questions that haunt the physicist's imagination. Can information, the most fundamental currency of reality, truly vanish? The laws of quantum mechanics forbid its destruction, even when matter collapses into black holes or dissolves into radiation. The paradox of information remains, like an ember that refuses to go out. Some theories suggest that every event, every interaction, every fluctuation is forever recorded in the fabric of space-time. Even when matter disappears, the information that defined it might remain imprinted, perhaps encoded in the holographic surface of the universe itself. If true, then even in the coldest future, the universe might still remember, not through stars or galaxies, but through the ghostly geometry of its own expansion. Others imagine a more final forgetting. If dark energy continues its acceleration unchecked, the expansion could reach a stage known as the Big Rip. In this catastrophic scenario, even the fabric of space-time would tear apart. Galaxies would disintegrate, solar systems would unravel, Atoms themselves would split under the strain of expansion. Gravity would lose not only its bond with matter, but the very arena in which it once ruled. Between these two destinies, eternal cold or violent dissolution, lies an even stranger speculation, that the universe, stretched thin by expansion, might one day reset. Some cosmologists propose that the vacuum energy driving dark energy could fluctuate, triggering a phase transition. A new universe might bubble into being, seeded by the decay of the old. If this occurs, gravity may once again find its voice, not as a force inherited from the past, but as a new geometry born from quantum foam. Perhaps every universe, as it forgets itself, plants the seed for another to remember. For now, these remain only possibilities, equations painted across the dark canvas of time. What is known is simpler and yet more haunting. As the cosmic expansion accelerates, the visible universe shrinks in meaning. The galaxies beyond our local group will fade beyond the cosmic horizon. Their light will never reach us, and from their perspective, we too will disappear. The cosmos, once a web of interconnected matter and motion, will fragment into isolated pockets of existence, each one unaware of the others. Communication, causality, memory, all will dissolve. The geometry of space-time will continue to expand, but without structure, without story. Gravity, stripped of its purpose, will cease to be a bridge between things. In this final act, the universe achieves perfect symmetry, not of beauty, but of indifference. Every particle drifts alone, every photon travels without witness. Time, unmeasured and unobserved, stretches into eternity. And yet, in the abstraction that remains, some see a strange grace. Gravity, freed from the burden of matter, becomes pure law, a ghostly architecture that no longer serves, no longer obeys, but simply is. It will persist as geometry, as curvature, as the idea of order in a place where nothing remains to be ordered. In the farthest mathematical future, when all physical forms have vanished, gravity may remain not as attraction, but as memory, the silent pattern of how things once curved toward one another. The universe will have forgotten the warmth of atoms, the glow of stars, the voice of galaxies calling across the void, but its shape, its invisible, faithful geometry, will endure like the faint afterimage of a dream. And in that final stillness, when even time loses its grip, gravity will remain what it has always been, not the pull of bodies, not the servant of mass, but the pure echo of existence remembering that it once was. It will no longer bend space, it will no longer bind matter. It will only drift, a faithless force set free by the silence it once shaped. In the final equations of the universe, something unexpected begins to emerge, not from matter, not from light, but from the spaces between them. The story that began as gravity's devotion to mass now turns inward, becoming less about attraction and more about meaning itself. Physicists and philosophers, confronted by the vanishing of the visible, begin to ask an almost heretical question. Was gravity ever real? Or was it always an echo? A perception born from the curvature of something deeper, more abstract, more profound. The first cracks in this old belief appeared not through mysticism, but through mathematics. In the 1970s, Jacob Bekenstein proposed that black holes, those absolute prisons of space-time, possess entropy, a measure of information hidden behind their event horizons. The insight was radical. If entropy represents the number of possible microscopic configurations of a system, then black holes too must carry information, even if none of it can escape. Stephen Hawking followed soon after, revealing that black holes were not eternal after all. Quantum mechanics demanded that they radiate, that their horizons shimmer faintly with thermal light. Yet this revelation birthed a paradox. If black holes evaporate, where does the information of all that fell within them go? Quantum law forbids its destruction, yet relativity allows no escape. In that contradiction, reality itself seems to whisper a secret. Information, not matter, may be the universe's most fundamental currency. From this seed, a new vision began to grow. A universe not made of particles and forces, but of relations and data. In the modern landscape of theoretical physics, thinkers like Leonard Susskind and Juan Maldacena suggest that gravity and spacetime themselves might emerge from the entanglement of quantum information. Their holographic principle imagines the universe as a vast encoded boundary, a two-dimensional sheet projecting the illusion of a three-dimensional world. In such a vision, matter and space are not separate entities. They are patterns woven from correlations in the quantum fabric. If this is true, then gravity, the gentle curvature of space-time, is not a fundamental force at all. It is an emergent phenomenon, a reflection of deeper informational order. It is the shape that data takes when it organizes itself into coherence. Einstein's equations, once written in the language of geometry and energy, might only be approximations of a more ancient rule. One written not in space and time, but in entropy and probability. Gravity, in this view, becomes a memory, not of matter, but of how matter once arranged itself. It is the statistical whisper of information seeking balance, the curvature born from the thermodynamic hunger of the universe to spread and equalize. And so the question deepens. If gravity emerges from information, what then is information itself? Is it merely physical? Or does it touch something that the language of physics cannot yet name? Some philosophers of science, following the trail of thought from John Wheeler's famous phrase, "it from bit," propose that the universe is not made of things, but of answers, binary decisions etched into the structure of reality. Each particle, each interaction, is a choice resolved, a yes or no, a 1 or 0 in the cosmic computation. In such a cosmos, existence is not substance but relation, not presence but pattern. Gravity, then, could be the geometry of those relations, a vast equilibrium among infinite yeses and nos, bending reality into the curves we call space-time. Quantum information theory reinforces this poetic symmetry. When two particles become entangled, their states intertwine beyond distance, their identities dissolving into shared correlation. This entanglement gives rise to connection, and in some modern interpretations, to space itself. If space-time is born from entanglement, then gravity is the manifestation of connection, the physical form of relationship. It is not force that holds the universe together, but coherence. Not mass that commands space, but information that shapes its possibility. In this light, gravity's betrayal of matter may not be betrayal at all. It may be transcendence, the evolution of reality from substance to structure, from weight to meaning. Matter decays, energy diffuses, but information persists, reshaping itself across the fabric of the cosmos. Even as galaxies drift apart and stars fade, the correlations that defined them remain encoded in the geometry of space. The story of the universe does not vanish. It reorganizes. The visible ends, but the informational continues, like ink, dissolving into water, yet leaving the memory of color behind. This reimagining transforms physics into philosophy. If reality is information, then observation too becomes part of its essence. Quantum mechanics tells us that the act of measurement alters the system being observed. Consciousness, or at least awareness, becomes woven into the equation. Some thinkers, such as Roger Penrose and David Chalmers, have wondered whether the universe's informational substrate might not only generate space-time, but experience itself. It is a dangerous idea to suggest that gravity, the most ancient and universal of natural phenomena, could be connected to the emergence of mind. Yet the parallel is striking. Both are born from connection, both depend on relation, both shape the structure of everything that follows. Consciousness curves thought as gravity curves space, and perhaps both arise from the same unspoken law, the tendency of the universe to bind what was once separate. In this landscape of speculation, the notion of separation takes on new meaning. The great schism between relativity and quantum theory, between the continuous and the discrete, between the smooth flow of space-time and the jitter of quantum foam, may be an illusion born of our limited vantage point. Gravity may not have left matter. It may simply have stepped into a higher form of unity, one that our mathematics has not yet fully learned to describe. The universe, seen through this lens, becomes an act of translation, from energy into geometry, from geometry into information, and perhaps from information into awareness. Each stage forgets the last, but carries its essence forward, like echoes evolving into music. When Einstein imagined gravity as the curvature of space-time, he gave the universe a shape. When Hawking and Bekenstein saw information as eternal, they gave it a soul. Between these two visions lies the modern frontier, a place where the physical and the philosophical converge. Here, gravity ceases to be a servant of mass. It becomes an interpreter, translating the unseen grammar of information into the language of form. In the halls of research, from the quantum gravity labs of Perimeter Institute to the black hole thermodynamics groups at Princeton and Stanford, scientists search for this unifying principle. Some seek it in strings vibrating through 11 dimensions, others in networks of quantum bits, where space-time emerges like a hologram from tangled relationships. Each attempt, however mathematical, is also metaphysical. An effort to understand not just what the universe is, but why it coheres. And as each model grows more intricate, the question becomes more subtle. Maybe the universe doesn't need matter to exist. Maybe it needs only memory. If information defines reality, then gravity's story is not one of loss, but of liberation. It no longer bends itself toward weight and density, but toward order and symmetry. It becomes the silent balance between entropy and coherence, a law without substance, a bridge without pillars. Perhaps then, gravity never stopped believing. It simply shifted its faith, from the tangible to the eternal, from matter to meaning. What began as a force may end as philosophy, a meditation on the way reality connects, forgets, and connects again. And in that vast transition, the cosmos may reveal its truest secret, that to separate is not to end, but to ascend. In the deepening future of the cosmos, silence becomes its dominant language. Galaxies recede beyond one another's sight, their light stretched until it fades into invisibility. The stars that once filled the night with their quiet fire now die one by one, leaving behind only embers. White dwarfs cooling into black, neutron hearts dimming into cold iron memory. The universe grows vast, yet empty, its expansion an accelerating breath that never ends. It is here, in this late age of time, that gravity's voice falls to a whisper. Once the architect of the grand cosmic architecture, the sculptor of galaxies, the binder of stars, the teacher of orbits, it now recedes into stillness. The fabric it once curved so elegantly begins to flatten, as if space-time itself has forgotten how to bend. The laws remain, but the actors that once obeyed them are gone. Matter dissolves, light thins, and gravity's devotion to the visible world fades with the last photons escaping into eternal night. Yet in that silence, something persists. Not in form, not in substance, but in structure. The geometry of the universe endures, an invisible lattice etched with the memory of everything that ever was. Even as black holes evaporate into Hawking radiation, releasing the final traces of their stored information, the pattern of what once existed remains. Every atom that burned, every orbit that curved, every collapse, every birth, all is preserved in the informational fabric that underlies space-time itself. Physicists once called this the holographic principle, the idea that the universe, even in its emptiness, keeps a perfect record of its own unfolding, not in the way a photograph captures an image, but as a mathematical truth woven into the horizon of reality. Every interaction leaves an imprint. Every moment, no matter how fleeting, becomes encoded into the expanding geometry of space. In this way, the end of gravity is not an erasure, but a transformation. The force that once governed mass becomes an echo, the residual memory of how information arranged itself when the universe was young and bright. What remains is not the warmth of stars, but the logic that once guided their birth and death. And so, the universe enters its final era, the dark energy-dominated epoch, a time when expansion defines everything. The once dense cosmos, born from a singularity of unimaginable compression, now races toward infinite dilution. Galaxies that remain gravitationally bound will drift in isolated clusters, surrounded by an ever-growing void. Beyond them, no new light will ever arrive. Communication between cosmic islands will end, not with destruction, but with distance. In the farthest reaches of time, 10 to the power of 100 years and beyond, even black holes will fade. The last anchors of gravity, those singular engines of space-time, will evaporate through the slow leakage of quantum radiation, releasing their stored entropy back into the void. The final act of gravity's story will not be a collapse, but a sigh, a long, gentle exhalation of all that ever was. And when that last whisper fades, what remains is equilibrium, a universe of near-perfect uniformity, filled not with stars or matter, but but with the quiet persistence of energy, the cosmological constant, dark energy, the ever-present pressure that drives expansion without end. It does not glow, nor bend, nor decay. It simply is. From this stillness, a haunting truth emerges. The universe was never built on permanence. Its foundation was always change, motion, decay, transformation. Even gravity, the force that once promised eternity, was a temporary expression of balance. Every galaxy that formed, every world that turned, every being that looked to the stars, all were shaped by an agreement destined to fade. But meaning, perhaps, is not found in what endures. It is found in the act of continuation itself. The cosmos does not preserve form, it preserves pattern. The wave may break, but the rhythm survives. Modern cosmology suggests that even in this emptiness, quantum fields still tremble. Virtual particles flicker in and out of existence, an infinite sea of ephemeral creation and annihilation. From these fluctuations, some physicists imagine new universes could be born, not from an external act, but as a natural consequence of quantum instability. The void, then, is not truly void. It is the seedbed of renewal, the silence between symphonies. Perhaps, in that distant darkness, another expansion begins, a new space-time blooming from the ashes of the old, inheriting not its matter but its mathematics, a universe remembering the rules of its ancestor, yet writing them anew. This idea that the universe may not end but recycle is not fantasy. In cyclic cosmologies, from Roger Penrose's conformal cyclic cosmology to models of eternal inflation, the end of one universe becomes the beginning of another. Each iteration forgets its past but inherits its structure. Gravity, once thought to die, may simply change its meaning, re-emerging in another form, in another geometry, in another story. The lesson hidden within these theories is quiet but profound. The cosmos does not cling to what was, it lets go again and again, and in doing so allows new meaning to emerge. The act of release is not loss, it is renewal. Humanity, standing at the edge of comprehension, looks upon this future not with despair, but with wonder. For to know that all things end is to recognize that all things are. The fleetingness of existence does not diminish its beauty, it defines it. The same equations that predict the death of stars also explain the light that once made them shine. The same gravity that will one day fall silent once sang the galaxies into being. In the stillness of cosmic night, one truth remains luminous. The universe has never been about permanence. It has always been about transformation. The collapse of stars gave birth to heavier elements, to planets, to life, to minds capable of asking why. The fading of light will give rise to something else. Perhaps new universes, perhaps only silence, but even silence too is a form of order. In this way, gravity's story is not a tragedy, but a transcendence. It began as attraction, the desire of matter to stay together. It ends as balance, the perfect poise between energy and emptiness. What once bent space now simply defines it. What once held galaxies close now releases them to their infinite destiny. And so, in the long twilight of the cosmos, gravity becomes a memory, a testament to connection, a trace of the universe's first language. It was never truly lost, only translated, from the pull of bodies to the harmony of equations, from the warmth of stars to the symmetry of information. Perhaps this is what remains when all else is gone, the quiet persistence of meaning. Even when light no longer shines and gravity no longer binds, something endures, and the pattern, the order, the invisible rhythm that once shaped everything, not a god, not a force, but a truth written into the architecture of reality itself, that the universe does not survive by holding on. It survives by letting go, and in that surrender, in that boundless expansion into silence, the cosmos completes the oldest promise of all, to remain not as matter or motion, but as memory, a geometry of existence still unfolding, long after the last star has forgotten how to burn.